is Will. This is my DATA605 final project. To begin, I started by loading in some necessary libraries. Next, I jumped right into creating my distributions. We have big X, which is a uniform distribution with 10,000 values ranging from 1 to n, and n in our case is 10. Then we have big Y, which is a normal distribution, 10,000 values, and it is centered around a mean, which is equal to n plus 1 over 2, which is also equal to 6.5, which is also equal to the standard deviation. Our little x is our median of big X, and our little y is the first quartile of big Y. We are using all these variables for our distribution probabilities, specifically to calculate these probabilities. It's straightforward and R, and these are our outputs. Next, we are going to create a contingency table. We want to show that the probability of big X greater than little x and big Y greater than little y is equal to the probability of big X greater than little x times the probability of big Y is greater than little y. If this holds true, then our distributions are independent. Otherwise, they are dependent. So we created a contingency table. You see here. Here we have our joint probability. Here we have our marginal probability. You see they are actually not equal, however they are pretty darn close, and I do have a hunch that they are going to be independent. Either way, let's go on and test for independence, which you should always do. In this case, we are going to be using Fisher's exact test and the chi-square test. Let's begin by stating our null hypothesis, which states that the variables are independent. There's no relationship between the variables. Our alternative hypothesis states that the variables are dependent and that there is a relationship between the variables. So whether or not we want to use the chi-square test or the Fisher's exact test does depend on the expected frequencies in your contingency table. So in our case, all of our frequencies are well over 5. 5 is usually the number I guess you have to keep in mind. If it's less than 5, you're going to want to use a Fisher's exact test. If it's greater than 5, you're going to want to use a chi-square test. If you do use the Fisher's exact test for larger samples, the downside is it could be a little bit more computationally expensive. So in our case, we would use a chi-square test. However, we're going to use both just because why not? So we get a p-value from our chi-square test of 0.204, which is greater than our alpha value, our threshold of 0.05. Therefore, we fail to reject our null hypothesis. This is stating that our variables are indeed independent. The same thing with our Fisher's exact test. We actually get the same p-value. We fail to reject our null hypothesis, and this also states that our variables are independent. Moving on to advanced regression for housing prices. This part we are really only using the training data set. However, I did load in both, but let's look at the training data set. You see it's 1460 by 81 columns, 1460 rows. And what I like about this, it shows you the data type for each column. Scrolling through, you see we have integers and factors mainly. Next, I took a summary of the training set that shows the the 5-number summary for each column as well as the factor levels. It's a lot to take in scrolling through. So next we are going to move to our correlation plots. So here I chose different factors that I felt might have a strong correlation with sales price. I chose the overall quality of the house, the square footage of the first floor, the greater living area, and the garage area. For the most part, they all have positive correlations, with the exception of a few which are kind of weak, hard to tell. But moving on, we are going to create our correlation matrix now. So our correlation matrix, this is the axis that we want to pay attention to, the sales price. This is our target variable. You see we have pretty strong correlation values, which is good. However, we do want to test if these correlation values are statistically significant, whether they're statistically significant or not. So we start by stating our null hypothesis, which says that the variables are independent and there is no correlation between variables. And our alternative hypothesis states that the variables are dependent and that there is a correlation between variables. We are going to test this statistical significance using the Pearson tests. We're going to be doing this one for each column, so a total of 4, using a confidence interval of 80%. We get p-values that are very close to 0 for each one. So in this case, we can reject our null hypothesis, and we can assume that these correlation values are statistically significant. But one thing to keep in mind is the family-wise error. This does have to do with what you choose as your confidence interval. So 80% is relatively low. And this gave us a value of 0.5904, which is very high considering we only ran 4 tests. This would increase too if we ran more tests, and it would increase if we decrease the confidence interval. However, our p-values were so small that we could actually use a 95% confidence interval, and we would still reject our null hypotheses. So that would reduce our family-wise error. If we ran it at a 95% confidence interval, it would reduce our family-wise error to 18%. And I guess just to touch upon the family-wise error too, this is kind of giving you a percentage of the likelihood of a type 1 error, which is a false positive. So it's pretty important to keep this pretty low. Or, sometimes you don't have a choice. But moving on, linear algebra and correlation. Here we are calculating our precision matrix. We are doing this using our correlation matrix. We are using the solve function from the matrix library. Here you see the precision matrix. Next, we are going to multiply this precision matrix by our correlation matrix, which gives us our identity matrix. Then we're going to multiply our correlation matrix by the precision matrix, and this is also going to give us the same matrix. We just double check this in R. We see that's true. Now we are going to perform an LU decomposition. In R, this is fairly straightforward. You start by creating the lower matrice and the upper matrice. Now we multiply the lower times the upper, and then we see that we get our original correlation matrix back. Now, calculate space probability and statistics. So we are going to create an exponential distribution using our greater living area training data. So we do this by using the fit_dist function from the mass library, and we call the parameter exponential because it's an exponential distribution. This gives us this object FD. From FD, we can call the optimal lambda value, which is FD estimate. With this optimal lambda value, we're going to be taking 1,000 samples. Then we're going to plot these 1,000 samples as a histogram alongside our original data. And you see how it changed. And now this allows us, just kind of leading to this, this allows us to calculate the 5th and 95th percentiles first of our cumulative distribution function. Here you see 77, 4,539, then our confidence interval of our empirical data that is assuming normality, so we scale it, and then we take the same confidence interval, we calculate the margin of error actually, and then subtract this from our means. And here you see our confidence interval. Next, we are taking the 5th and 95th percentile of our original data. The last part of the assignment is to create this regression model. We are loading in the same data sets again. We already looked at the training, so this time around we're going to look at the test data set. You see here it's one less row and one less variable. I believe that's true. Let's double check. Yes, okay. So it's one less row, one less variable. Once again, it is all factors integers. We are going to take the summary of the test data set, scrolling through. Now we're going to take the log value of our the sales prices in our training set. This helps with regressions. It helps increase your adjusted R² score. Next, since we are missing a column, it was actually the sale price column. So we're going to create that column and set it equal to 0 for now. We are going to convert the non-numerical columns to factors for both the training and test data sets. And then we're going to set our NA values equal to 0. This allows us to actually create those predictions, and eventually we're going to submit it to Kaggle. So it's necessary. We make sure that there's no more NA values. Now comes time to train the model. We use a step AIC function, once again from that math library. We are doing a forward stepwise process, and this is pretty much taking the lowest p-values and it's adding it to the model, and it's pretty much giving you the highest R² possible, adjusted R² possible. You see here our adjusted R² was 0.8868161. I actually did a different model, and it did come up with a higher adjusted R² value. However, I come to find out it looked like the model was overfit, but that's besides the point. So here we're going to plot our residuals of our model, and we kind of want to get an idea. We want to make sure that it's random variance. So we do see our quantiles plot is along our line, which is good. The residuals, our fitted values plotted against our residuals, it's pretty random, the variance. Our histogram of residuals is pretty uniform, and our residuals as we collect the data is also random in variance. So all of these are good signs. So lastly, we use our model to predict the sales prices in our test data set. And then we, just to make sure, this is pretty important, you can't forget this, that once we get these predicted values, we have to take the exponential value, because originally, looking back, we took the log, where was it? It's all the way up there, so yeah, here it is. So we took the log of the training set sales price, and that's how we fitted the model, using the log values. So we have to remember to turn it back by using the exponential function. I submitted this to Kaggle, and I got a score of 0.14318. That's about it. I kind of fell in the center of the pack in Kaggle, which I'm not thrilled about, but it is something I'm going to experiment more with different models, and you know, it was already a great learning process for me, so I'm pretty proud of it. But yep, and that's my presentation. Thank you.